And what we're going to talk about today is using quantitative methods, so using statistics to estimate causal relationships. How one thing causes some change in something else, or the effects of some intervention. And I'm going to start today's program by making two bold claims, which for the sake of dramatic effect, I am not going to qualify, even though there are obvious counterexamples and the claims are by no means universal, but I think they are more universal than we might think they are. So my first bold claim is our questions are causal. In education research, our questions are causal. We are interested in how certain actions we can take can lead to some sort of change. And we can see this in the language that we use when we ask our questions. And oftentimes, right, the first couple of years of grad school, you're learning how not to ask a question in a causal way. Right, so some causal questions are, what is the effect of a reading program on reading levels? Right? If we institute this new pedagogical approach to reading, how does that change reading levels of students? A second causal question from a higher ed perspective is, does simplifying the FAFSA form cause more students to complete the FAFSA? Does shrinking it from however many pages it is now down to 1 page or a postcard or whatever it is the Congress wants to do, does that lead to more students completing the FAFSA? How the change in the FAFSA causes this outcome? And then the final example here I have is, what impact does school finance have on student learning outcomes? If we change the funding models of schools, does that change some sort of outcome? Does that change the amount of learning students have? Does that change graduation rates? Does that change attendance? Right. I do want to put I said impact here because that's a common word, but I also want to put out my own disclaimer of, I'm opposed to using the word impact in research questions like this. It has physical connotations that I don't like, but it also has causal connotations, right? So if you all don't mind, I would like for everyone just to type into the chat a research question that you have that you think might be causal. Right, something that's been mulling around in your mind, and it doesn't have to be worded perfectly, right? But just something that's been mulling around in your mind that you think is causal, where a change in one thing leads to a change in something else. I'll start with another one of my own examples. So I put in one of my own research questions that I have, which is, what is the effect of university community engagement initiatives on local rent? And by rent, I mean quite literally the price people pay to a landlord to be able to live in a certain accommodation, right? So how do university steps change rent? Looks like we have some people typing. These don't have to be highly polished. So here we have from Priscilla, to what extent does student involvement impact student graduation rates and retention? Yes, exactly. How does participation, both in the classroom, outside the classroom, how does that change? How does that affect graduation and retention? Right, that is some concrete outcome that is a result of some action we have taken. All right, let's see if we can get one more. To what extent do compensation incentives impact superintendent tenure? Yes, so how the salaries that we pay, or the end of year bonuses, or any other type of incentive, how does that change superintendent tenure? How does that change how long the superintendent stays in a specific position? Yes, good job, excellent. So these are great examples of how our research questions in education are inherently causal. And now for my second bold claim. Even though our questions are causal, our research is not. So we have to use specific methodological approaches to make causal claims, which we very often do not. Right? So for those of you who have taken intermediate statistics, multiple regressions can tell us there is a relationship or is an association between variables. And those are words that don't have causal connotations. Those are words that are okay to use when you don't have a causal design. And a multiple regression can even tell us there's a relationship after conditioning on some other set of variables. So for example, the relationship between high school graduation and wages, we can use a multiple regression to say what the relationship is between graduation and wages, even after conditioning on things like GPA or family income. But it's still not causal. We still can't say this is the concrete effect of wages of graduation. We can't say that high school graduation leads to, an increase of $20 per hour or $15 per hour without using a causal design. Right? So there's the old adage, which is tired and annoying, but it is also true that correlation does not equal causation. So even though we know that there's a relationship between high school graduation and wages, we don't necessarily know that that is a causal relationship, that high school graduation causes your wages to go up, right? Because there's a whole host of other things that will affect both high school graduation and your wages. One of those that I mentioned earlier is family income. If you have a high family income, you're more likely to graduate from high school, and you're also more likely to have higher wages. Right? So it's hard to parse out what the effect is of high school graduation because of all these other unobserved variables that are going on. So those are my two bold claims that we're going to talk about today. First, that our questions are causal, and second, that our research is not. And so now I plan on positing how we can do causal research, how we can answer these causal questions. So first we need to clarify, what is a causal relationship, right? And we could have a whole seminar, probably a whole course on this question, but I'll leave that to the philosophy department. You can talk to them if you want to get into the details. Today we're going to talk about the prevailing answer in the social sciences of and how we currently conceptualize causal relationships. So what do we mean by cause and effect? So let's think about an obvious example first of hitting a cue ball with a pool stick, or whatever those things are called, pool poles, or I don't know, I don't play pool. So we hit the cue ball with the pool stick and observe the ball move, right? I think we'd all agree that that is a causal relationship. We can say it's causal for two main reasons. First, the cause preceded the effect. So first, the ball did not start moving before the stick hit it. In some strict understandings of causal relationships, we would also note that the ball started moving immediately after being hit. So there wasn't a pause between being hit by the stick and the ball moving, though oftentimes in social sciences, we're less concerned about a little bit of lag. So a little bit of lag is okay for our purposes. But so the stick hit the ball and then the ball moved. So the cause preceded the effect. And then the second reason we can say that it is a causal relationship is because there are no other plausible causes. There simply is no other good reason why the ball would move at that exact moment other than it being hit by the stick. So if we imagine a world, okay, so a whole new world, this is a quantum multi-universe type thing. We have another world in which we did not hit the cue ball with the stick. The ball would not have moved. I feel fairly confident in saying in this imaginary world that is as similar to ours as possible, except you did not hit the cue ball with the stick at that moment, the ball would not have moved. And so those are the two criterion for cause and effect in this case. One, the cause preceded the effect, and two, in an imaginary world in which the stick did not hit the ball did not move, or the ball would not have moved. Okay, so let's think of a slightly more complicated example now. So imagine the bell rings at your school at 3 o'clock in the afternoon, and all your students get up and leave. So can we say that the bell caused the students to get up and leave? Using your reaction tab, give me a thumbs up if you think that's a causal relationship, and give me the shocked face if you think it's not a causal relationship. So we've got a few thumbs up. I think I saw one shocked face. So let's think about our two criterion for a causal relationship again. First, did the cause precede the effect? So do you think that the bell rang first and then students got up and left? I told you that's what happened, so that's what happened. So you know that anybody who's been in a middle school or high school knows that's not always the case. But so the bell rings and then students got up and left. So check, meets our first criterion for cause and effect. The second criterion gets a little trickier. So is the bell ringing the only possible cause for students to get up and leave at 3 o'clock? So let's imagine our other world, right? Our imaginary world in which the bell does not ring. So everything about the world is exactly the same, except the bell did not ring at 3 o'clock at the school. Now we ask ourselves, do students still get up and leave at 3 o'clock? I would say maybe, but it wouldn't be as synchronized across the whole school, right? A bell rings, everybody gets up and leaves at once. Whereas if there is no bell, students would probably start standing up around 2:58, 2:59, you know, start like inching toward the door while the teacher's still talking, you know, kind of cluster around the door with their backpacks on. Or everyone leaves when each individual teacher across the school dismisses the students. Right? So with the bell, everyone gets up and leaves at the same time. Whereas without the bell, everyone still gets up and leaves around 3 o'clock. It's just not as synchronized, right? So we might say the bell does not cause students to leave generally, because students would have left around 3 o'clock no matter what, but it does cause everyone to leave at the same time. So what actually causes students to leave at 3 is the knowledge that school lets out at 3. Right? If we imagine a world in which students don't know that school lets out at 3, then they don't all get up and leave at 3. They leave at whatever time the teacher tells them now is the time to leave. But since they know they leave at 3, that has caused them to leave around 3, no matter what. And then the bell additionally causes everyone to get up and leave at about the same time. Right? Okay, one last example. So the bell rings at your school at 3 o'clock in the afternoon, and a barista at a coffee shop across town packs up her stuff and leaves. Leaves her work, leaves the coffee shop. So give me a thumbs up if you think that's a causal relationship. Give me a shocked face if you think it is not a causal relationship. Bell rings at the school at 3, and a barista leaves work across town. Yeah, I'm getting shocked faces. Yes. So this is not a causal relationship. Let's go through our two criterion. Does the cause precede the effect? Yes, because I told you. The bell rings at 3, and then the barista across town leaves work. Check. But our second criteria is the sticker here, right? Is the school bell ringing the only plausible cause, or is it a plausible cause at all, for why a barista would leave work across town? So let's imagine our world, right? Imagine our world in which the school bell doesn't ring. Does the barista still leave? Almost certainly, right? Maybe their shift is over. Maybe they're feeling a little sick and 3 o'clock was the earliest they could get out, right? What almost certainly did not affect their decision to leave is the school bell going off. So this imaginary world we keep thinking of, where everything is the same except for our cause, is what we call a counterfactual. So the counterfactual is, this is actually a pretty common concept in philosophy that we have co-opted in the social sciences for the purposes of causal research. The counterfactual is a world as similar to ours as possible, where the only change is the cause did not occur. Right? Whatever our intervention is that we're interested in did not occur. And so here are just 3 different examples tied to the causal questions I presented earlier of, in the real world, a new reading program was implemented. We changed how students approach reading, let's say in 1st grade or whatever. And then the counterfactual, so the world that is as similar as possible except the cause did not occur, is the students just stick with the old reading program that they were using before the intervention was implemented. Same with the FAFSA. So in the real world, the FAFSA is simplified, and the counterfactual is the FAFSA remains the same. So I think it's important to note here, sometimes we think of a counterfactual as the complete absence of something, but that's not really the case. It's just that the old way of doing things remains the same. Right? And then the final example I gave was that school finance models change, and the counterfactual is school finance models remain the same. So I'm not going to ask you to put this in the chat, but I just want you to think about those research questions that you put in the chat earlier, and think about if in the real world, this change was implemented, just think to yourself about what the counterfactual is there. So we have the real world, and then we have the counterfactual. The effect of some cause, so the effect of the reading program, or the effect of simplifying the FAFSA, is the difference between the real world and the counterfactual. So whatever happens in the real world that did not happen in the counterfactual is the effect of that change, is the effect of that intervention. So are reading levels higher in the real world, where students went through this new reading program, or are they higher in the counterfactual, where they continued using the old reading program? And that difference, we say, is the effect of the reading program. So this is, at the most intuitive level, what we're trying to get at with causal designs, is the difference between the real world and the counterfactual. So how do we measure that difference between the real world and the counterfactual? Ideally, we'd use a time machine. We would implement the new reading program. After a year, we would measure the reading comprehension of the students, right? Maybe it's some form of standardized test. Maybe it's asking the students to read a book and write some sort of book report or something at the end, however we want to measure it. So we've measured reading comprehension after the new reading program. Then we hop in our time machine, we go back 1 year, and then we keep the old reading program and measure reading comprehension for those same students. So we would have the measure of the new reading program for students compared to the old reading program for those same students. And the difference between the real world and the counterfactual would be the effect of that reading program. I think you see the problem already. I have no knowledge of a time machine in existence, right? So instead of measuring the counterfactual, we estimate the counterfactual using a control group, right? And when I say control group, I'm talking about the when you learned about the experimental design in middle school science classes, right, where you have a treatment group and a control group. That's what we're talking about here. We estimate the counterfactual using some sort of control group that we want to be as similar as possible to our treatment group. And so the set of causal methods that we're going to talk about in the second half of this talk are essentially just different ways to build a control group that we think is as close to the counterfactual as we can get. Which, remember, the counterfactual would be those same people who received treatment, but in this imaginary world did not receive treatment. And the best way that we have to get a control group that is as close as possible to a counterfactual is what we call the randomized control trial, or the RCT. So RCTs, you might have heard them called the gold standard of research, right? And these are, if you were following clinical trials during COVID, right, those were RCTs. So what is it about an RCT that makes it so desirable? So there are two defining features of an RCT. The first is that treatment is manipulated by the researcher. So the researcher or the research team has full control over who receives treatment and who does not receive treatment. So let's imagine the reading program. The researcher would have full control over which students participated in the new reading program and which students did not participate in the new reading program. And then the second defining feature of an RCT, and most important for us, for our purposes today, are that participants are randomly assigned to the treatment or control group. Right. So what that looks like in an experimental design here, we have two groups. Let's say we had 100 first graders participating in this experiment. We would randomly assign 50 of them to the treatment group and randomly assign 50 of them to the control group. It doesn't have to be balanced like that. It's okay if you have more people in the control group than in the treatment group, but if you have full control over it, you might as well even it out, right? So you have 50 students randomly assigned to the treatment group, 50 students randomly assigned to the control group. And then at time 1, you administer the treatment, or you introduce the intervention, which in this case is the new reading program. And so 50 of the students receive this new reading program, 50 of them just go through the normal old reading program. Right? And it's important that the control group is as close to the counterfactual as possible. Yes, so RCT stands for randomized control trial. So randomized control trial. So what you don't want to measure is a control group that receives no reading education at all, right? Because that's not the counterfactual. The counterfactual is not that students don't receive any sort of reading education. The counterfactual is students receive this old type of reading program. And so we've administered the treatment. 50 of the students have received the new reading program. And then at time 2, so let's just say at the end of the academic year, we measure reading comprehension for both the treatment group and the control group. And then the difference between those two is the effect of the reading program. So there are different ways to design an RCT. This is the most standard, right? This is the this approach would be very common in disciplines like biology or something, where a petri dish of E. coli is very easy to get, and it's very easy to randomly assign E. coli to two different petri dishes, right? So this type of design is very common, and you'll see it in some education studies too. But there are different ways to play around with when you measure who receives treatment. But this is the basic layout of the most important parts are random assignment prior to treatment, and then some people receive treatment, others don't. Measure both, the difference between the two. So what is it about random assignment? Why do we care so much about randomly assigning people to either treatment or control? So without random assignment, we're concerned with what we call the selection problem. So if participants can choose whether they are in the treatment group or whether they are in the control group, there are going to be unobserved characteristics that determine which group they select into. And these characteristics are very likely to affect the outcome of interest. So let's take, for example, a leadership training program. Let's say that, let's imagine we're on a college campus and there is some sort of leadership training program for undergrads. And these types of leadership training programs, they're usually just things that people select into. A student chooses to participate in this leadership training program. We can't randomly pull students from campus and automatically enroll them in this leadership training program without their consent, right? And so since people select into this leadership training program, people with higher proclivities for leadership are more likely to participate in this leadership training program. There are things like you have an interest in learning, right? I think that's a desirable quality in a leader. That is probably the type of thing that is somebody who enjoys learning or has an interest in learning is more likely to enroll in this leadership training program, right? There are also people who enroll in this leadership training program are taking an initiative to participate. That is a trait of a leader. That is a trait that that person had prior to enrolling in the leadership training program, right? So those are things that are going to affect whether you participate and affect how you score on however we measure leadership at the end of that training program, right? So if we were to just compare people who chose to participate in a leadership training program to people who chose not to participate in a leadership training program, we would very likely find some sort of difference, right? And that difference could be completely unrelated to whether that person participated in the program or not. So that's one thing, is participants will choose to be in the treatment or control groups based on pre-existing characteristics. And then the second thing is oftentimes treatment is decided through some other non-random mechanism outside of the control of the participants themselves. So, for example, this new reading program we've been talking about. Let's just say that first graders had no say over which reading program they participated in. I don't remember I ever had any control over my reading program in first grade. The principal might choose which classrooms receive this new reading program. Maybe they choose the classrooms that have the lowest scores as a way to help bring these students up and create a more egalitarian school, right? Maybe they choose the classes with the highest scores because for whatever reason, this principal has a vested interest in this reading program and really wants it to succeed, right? And so these are things outside of the control of the participants that can also still change the results of the experiment, of the RCT, right? And there are very good reasons for doing these things, right? Maybe I think it's admirable to try new things in classrooms that are performing more poorly, right? Another example would be policymakers are deciding which school districts will get private school vouchers, right? There's a whole host of causal research on the effect of private school vouchers. There's honestly probably too much research on the effects of private school vouchers. And how these private school vouchers are implemented is often not random, right? Maybe the superintendent or the policymaker who's deciding these things has settled on the lowest income school districts as being the place where private school vouchers are given. Maybe they settle on areas that have good private schools. That would make sense to me, giving private school vouchers in areas where students could use them at good private schools, right? So there are good reasons for these things for non-random assignment that just make our job as researchers more difficult. But random assignment resolves these concerns, right? Because there are no systematic differences between the treatment group and the control group because we know how it's been assigned and it was randomly, right? So this is, there's some qualifiers to this, statistically, probability speaking, but for today, it's fair to say that there will be no systematic differences between the treatment group and the control group if you have randomly assigned, because any reason why you would seek out treatment is washed away. It doesn't matter if you would have seeked out treatment because you were randomly assigned to it, and you might have just as easily been randomly assigned to the control group. And so that's why random assignment is so good at getting us that counterfactual, that imaginary world where everything is the same except the cause was not implemented. Because you are just as likely to end up in the control group as you are in the treatment group, no matter what your pre-existing characteristics are. So those are RCTs. That's the gist of RCT. And there's a lot more that would go into it. And if you're interested in doing an RCT, I would encourage you to read more about it. The problem with RCTs, there are a few problems, two of which I'll say before we move on. One is they're very often expensive. They're expensive and time intensive. So it's difficult to do a good RCT. And then the second main issue with RCTs is they very often suffer from external validity concerns, which you might remember. External validity is the degree to which we can generalize to a larger population. But since RCTs are so controlled, it's very difficult to generalize out to a much larger population. One, we have to take volunteers for an RCT. You can't coerce people to participate in an RCT, right? And so you've already got that one pre-existing characteristic that you can generalize out to the population of people who would have volunteered to participate in an RCT for whatever reason, right? So they have these generalizability concerns. Which brings us to natural experiments. And this is what the Nobel Prize winners won for, basically, is different methods that allow us to draw causal conclusions, to make causal claims using secondary observational data. So natural experiments are a set of methods that allow us to make these causal claims without us, the researchers, having control over treatment assignment. So instead of randomly assigning participants to either treatment or control group, there has been some sort of treatment that happens out in the world, outside of our control. And then we use observational data. So it generally is secondary data that exists already, right? Like administrative data, something like that, instead of the experimental data that we generate. And so the trick with the natural experiments is, since we don't have random assignment, we have to use other ways to try to approximate that counterfactual, that imaginary world. And the way we do that is we try to approximate random assignment. And I'm going to go over two different ways that we try to do that. The first is what we call difference in differences, and the second is what we call regression discontinuities. So difference in differences is probably it is the most common form of causal research that you're going to see. Difference in differences is, if you were to pull up any journal that regularly publishes causal research, probably each issue has at least one difference in differences study. So without true random assignment, right, without us randomly saying treatment group, control group, treatment group, we can't say that the treatment and control groups are the same. We just don't have that ability to say that this treatment group and this control group are basically the same, or at least they would have been the same if it weren't for the treatment. We don't have that ability. But what if we can say that the change in the treatment group and control groups are the same? Or at least the change would have been the same were it not for the treatment. So this is the difference between, with random assignment, we can say basically that the levels, let's say we're interested in GPA, we can say that the levels of GPA in the treatment group and control group are the same. But with difference in differences, we're not concerned about levels. Now we say that the change in GPA is the same, regardless of what the level is. And this is an easier assumption to meet. It's still tough to meet, but it's an easier assumption to meet than saying the levels are the same. And this is what we call the parallel trends assumption. I think I skipped a slide. Yes, okay. So the parallel trends assumption says that the treatment group and control groups would have experienced identical change in the outcome were it not for the treatment. So if GPA increased 0.1 in the treatment group, we are saying that it, if it increased 0.1 in the control group, we're saying it would have also increased by 0.1 in the treatment group were it not for the treatment. And there's two convincing ways to show that you meet the parallel trends assumption. First, were the trends parallel prior to treatment? If you look at the two lines, if you were to graph them a long time and they moved along with each other, then that's a pretty convincing argument to me that yes, the trends are parallel, right? And if there was treatment and one skyrocketed off and one stayed the same, I would say that's a pretty good evidence of an effect. And then the second and the more convincing way is that just for whatever reason that happened out in the real world, treatment assignment just happened to be random, right? So private school vouchers are a good example. A lot of private school vouchers were given to students via a lottery, right? So treatment assignment was still random. It was with a lottery. And so we can use that to say that, yes, we meet the parallel trends assumption because treatment assignment was still random, right? But in a lot of cases, we don't have that random assignment. So if you can show that trends were parallel prior to treatment, you're going to be in good shape. So why does this work? So let's say we introduce some sort of intervention that we expect will raise GPAs. Let's say it's like a nutritional breakfast or something. So we have on the left our GPA values before we introduce the nutritional breakfast, and on the right we have our GPA values after we introduced the nutritional breakfast. And the orange is the treatment group and the blue is the control group. So the school at the top, we can see has higher GPAs overall, but let's assume that the trends are the same. So changes in GPA at the first school always mirror changes in GPA at the second, just at different levels. Right, so if at the top school let's just say the average GPA was 4.0 and it dropped down to 3.8 at the second school, their average GPA might be 3.0 and it would drop down to 2.8. Right? So what we really want to measure here is the difference between points B and E. So E being the counterfactual, being the GPA at this school where a nutritional breakfast was never introduced. They had, like, powdered donuts every morning. So algebraically, the difference between B and E is the same as finding the difference between the change across time from A to B as the change across time from A to E. But we don't know E, right? We don't observe this school not getting a nutritional breakfast. We only observe this school getting a nutritional breakfast. So instead of calculating the change across time from A to E, there on the bottom, we measure C to D at the other school. So even though the line above is higher, even though the level of GPA is higher, the change from C to D is parallel to the line from A to E. The change is the same were it not for the intervention. And so we measure the change across time for the school that received the intervention, the change across time for the school that did not receive the intervention, and then the difference between those two differences, so the difference in differences, gives us the effect. And if we meet the parallel trends assumption between the real world and the counterfactual, we have the effect of the nutritional breakfast. So just to show you a little bit more about what I mean by difference in differences, we have difference 1, which is how the outcome variable changed from time 1 to time 2. Difference 2, which is how the control group changed from time 1 to time 2. And then we find the difference between those two. So the difference in differences. And that third difference is going to tell us the effect of this treatment. So what happens when our trends aren't parallel? So this is a cautionary tale. So our school at the bottom is exactly the same. They received the nutritional breakfast, and in this world, it caused an increase in GPAs. So in the real world, there actually was an increase in GPAs. But let's say we chose as our control group a school that did not meet the parallel trends assumption. We chose a school where the change in the top school did not mirror the change in the bottom school, were it not for the treatment. And so the difference between C and D is not the same as the difference between A and E. And so our estimated effect here is not equal to the true effect. We are going to massively underestimate the true effect of the nutritional breakfast. We might even say, just eyeballing this, we might say that there was no effect of the nutritional breakfast, even though there actually was. And that's because we did a poor job of approximating the counterfactual in this case. And so for those of you who have taken intermediate statistics, and for those of you who are going to take intermediate statistics, we can do this in a regression model. If you have if you truly meet the parallel trends assumption, you can truly just subtract and you'll get a causal effect. But we're usually pessimistic that we have truly met the parallel trends assumption. So what we do instead is we use a regression. We put our diff and diff into a regression model, which allows us to control for other variables that we think is changing the slopes of the lines, the slopes of those trends. So just for example, there might be a huge number of things that affect the trends at the top school and the bottom school. So things like maybe property taxes at the top school are higher, or they became much higher at the same time the nutritional breakfast was introduced, right? So with a regression, we can include those things and control for them, which weakens our parallel trends assumption. But the basic format is we have one variable that is the treatment variable. It's either equal to 0 if you're in the control group or 1 if you're in the treatment group. We have this post variable, which is equal to 0 if you're in the pre-treatment period or 1 if you're in the post-treatment period. And then we have this what we call an interaction term, which is where we multiply together treatment and the time variable. And beta 3 is going to be exactly the same as if we just subtracted. But then if we control for the other variates, it's going to change beta 3 because it's going to be beta 3 after controlling for these other variables. Okay, so that is the quick and dirty difference in differences. A few caveats is, so this is what we call the canonical model of diff and diff, where we have one treatment group, we have one control group, and the intervention happened at one point in time. And this is still, if that's what you have, you can 100% use a diff and diff if you meet the parallel trends assumption, and you're going to get a causal effect. There is also a way to do diff and diff in regression if you had treatment at multiple time periods. So you have a treatment at time 1, and then a few years later you have another treatment at time 2, a few years later another treatment at time 3. And that was all the rage for a decade or more. But over the last couple years, we have learned a lot more about how that changes our estimates. And it's becoming a lot more complicated. There's a lot more things that you have to do in order to make sure that your estimates are correct. So if you have something more complicated than this canonical model, that's okay. That's still good. Just know that there's going to be a little bit more to dive into on that. So then the final method I want to cover today is what's called a regression discontinuity. And I really like regression discontinuities because they're so intuitive. A diff and diff is intuitive also. I think maybe a little more intuitive, but a regression discontinuity is also very intuitive and is very powerful for getting causal effects. So the way regression discontinuities work is they rely on a treatment being assigned by some cutoff point along some continuous variable. So let's imagine a college, right? And a college that has the most simple admissions policy ever, where it will admit every student who receives a 15 on the ACT. So if you're a student, you receive a 15 on the ACT, you are admitted to that college. So what a regression discontinuity assumes is that students who just missed the cutoff, so students who made a 14 on the ACT, are going to be essentially identical to students who just made the cutoff, so who received a 15 on the ACT, for example. Right. And so those students who just missed the cutoff now become the counterfactual to being admitted to college. And so now let's just say that we're interested in wages. We can measure the wages following college graduation. Apologize, 1 second. We can measure the wages of students who were just barely admitted to that college to students who just barely missed admissions. And then we could say this is the effect on wages of being admitted to this college. So let's see, this is what it looks like, right? So along the bottom, we have our assignment variable. So let's just say this is your ACT score, right? And then along the left, we have the outcome variable, sorry. Along the left, we have the outcome variable. which let's just say this is wages. I'm going to let it ring this time. Okay. And so what a regression discontinuity assumes is that students who are between a 6 and a 10 on the ACT along here, right, maybe they just missed a few questions on the test. And we would argue that missing a few questions on the test does not make that student inherently different or systematically different from students who just happen to get those few questions right. Right? And so the students who just missed the cutoff serve as our counterfactual. And then this is what it looks like with a regression if you're interested, where we have kind of just the standard specification. We have no covariates, where we have this treatment variable equal to 1 if you are treated, equal to 0 if you just missed the cutoff. And then we have to include what we call the running variable, which is that continuous variable. So in our ACT example, you would be equal to 1 if you received treatment, if you were admitted to the college, be equal to 0 if you were not admitted to the college, and then we would also include your ACT score. And then also, again, the neat thing with regression, which for those of you who haven't taken intermediate statistics yet, it's going to rock your world. We can also include covariates, right? So we can say this is the effect. So beta 1 would be our effect of being admitted to college after controlling for this set of covariates. So it's not only random assignment or as good as random assignment because some people just made the cutoff and some people just missed the cutoff, but we also control for this other set of variables that we might be concerned about. And so we call beta 1 the local average treatment effect, or the LATE. And why we call it the local average treatment effect is because our generalizability with regression discontinuities is limited to the participants around the cutoff. Because the further away you get from the cutoff, the more different the students get. Right? So a student who makes a 15 on the ACT and a student who makes a 14 are essentially identical. And you can start to make the argument students who make an 18 on the ACT might be essentially identical as students who make a 13, right? There's no hard and fast rules for how far away you can get from the cutoff. But once you get to students who make a 30 on the ACT compared to students who make a 2 on the ACT, there's going to be some sort of systematic difference, right? There's probably going to be income differences. There's going to be support differences at the high schools that they went to, right? There's going to be all sorts of systematic differences where students who missed the cutoff are no longer a good counterfactual to students who made the cutoff. And then the last concern with regression discontinuity that is becoming more of a concern in the last few months actually is participants with knowledge of what that cutoff is are going to make a little bit extra effort to pass the cutoff, right? So a student who scores a 14 on the ACT, but knows I need a 15 to get into this college, and their family has the resources to both know that that cutoff exists and to know how they can improve their score, those students are going to go that extra few inches just to make the cutoff, right? And that is going to make them systematically different from participants who don't have knowledge of the cutoff or without the resources. They may know the cutoff exists, but they don't have the resources to make that extra push, right? And that leads to what we call bunching or clustering, right? Where you tend to see participants get real right close up to the cutoff and people that are real right close to just making it. And it's all about who has knowledge of what that cutoff is. And so if you do a regression discontinuity, that's something you want to be concerned about, something you want to keep an eye out for. So those are 3 different methods for causal designs, right? For getting answering causal questions. We have, just to go over, RCTs, randomized control trials, diff and diff, which was difference and differences, which I think is probably the most likely to, if you all are here for your dissertations, that's probably the most likely to be a successful and good dissertation, at least easiest to grasp. And then regression discontinuity, which if you have a good cutoff point, you have a good running variable, regression discontinuity is going to be a super powerful design, but sometimes they can be hard to find. So I just wanted to conclude today, too, by encouraging you all to think about whether your research questions that you're interested in are implicitly or even explicitly causal. So think about those research questions you put in the chat. Think about the research questions you're mulling over in your work, in your programs. And if they are causal, whether you think they're just implicitly causal or whether you truly are interested in capturing an effect, I would like for you to seriously consider whether there's a way for you to implement a causal design, right? Whether there's a way for you to do a diff and diff, whether there are data available for you to do a diff and diff or a regression discontinuity. But I also wanted to say we don't always have the data we need to use these designs for some of the most pressing issues facing us in education today, and that should not prevent us from asking those questions. Right, so there's a story I want to close with about a person who lost their car keys in the middle of the night, and they were only looking under the lampposts. Right? And when somebody came up to them and asked, why don't you try looking literally anywhere else? You haven't found your car keys yet. And they said, because under the lampposts is where the light is. Right? So don't only look under the lampposts. Causal designs are great lampposts. They are going to shine excellent light on the ground underneath of them. But if you have an important causal question and you make a good faith effort to use causal designs, but the data just aren't there, don't let that stop you from asking the question. You're just going to have to be a little careful around how you frame it. All right, thank you very much.